All right, so on to the last, probably the last um, setup for the blue stuff is the environmental kickup, environmental smoke kickup. You see all these smoke that gets kicked up off of the assets I have around the environment. So the setup for this is not too difficult. It's under the blue source dust kickup faint. There's another one called the dust kickup. I'm debating whether to go over this as it doesn't add a lot to the overall look. So leave this out for now and we'll focus on the dust kickup faint. So this is how it looks. So actually I've separated this into two different sims. One is um, the left side and the other is the right side. So they're all running on through the same solver that I have to update, by the way. So I'm just going to duplicate this and 3.1. So they're all running through the same solver, the same settings, and everything. But the interesting part is how we got to getting the source. So I'm just gonna keep this. No. Geometry pixels. Oof. So I want to show how I got the timing for the radial blast. Is through this zoom, 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 and it's not that difficult. So first things first. Okay, so unfortunately I won't be able to share with you guys the asset that I am using for the project, but I'll show you how I've done these parts. So I've got this effector mask that is just like a gradient mask from the impact point and with a fall off towards a certain distance. Okay, and then in here I'm just calculating the gradient of that mask. So if you just put grad on to our normals, and we can see that we've got these vectors coming out from the impact point and it flows along the asset. We just scale down our normals a little bit just to see things better. So you can see we've got these normals like flowing along our assets, our environment. If you can see this, it goes up and flows all around. Cool. So that's through a wrangle. And so I want to just quickly explain how I calculated the gradient for a float attribute. So I've just put this like grid little example scene. So I've got these nice. So we've got this scene and just want to scatter a bunch of points and remove the relaxed iterations and just keep that there. And I've got this little node, a factor mask node. It's just essentially like a attribute transfer, some initial attribute onto the points. So if you see, like, I've scattered some points on the environment and the floor, and I've got this the blue start point, and just using that to transfer. But we can use another method. It's a node called distance from target. We just put that down there, and we put output mask, and we take this on. So we see we've got this little mask now that we can offset using these controls. Cool. But our impact point starts at the origin anyway, so we just put it here. We can see how much radius we want to have. Let's expand our scene a little bit, like that. Now we can see we've got some cool gradient mask to our little thing. That's pretty awesome. Maybe some more points. Cool. Now, so we've got this. So essentially what we want to do is remap. So this mask attribute, check the mask attribute, is a normalized attribute. It basically is from 0 to 1. That's very useful for us because we can easily just remap that with a start frame. So if you just put mask, create a new name, start frame, and set that to probably try from 10, 15 to, oops, 10, 15 to 10, 20. Nice. And we say, so that does nothing for now, but we'll say probably okay. If the current frame is not equal to the start frame, then we remove the points. So what we expect is something like this, which is not really what I want to see, because this is wrong. Let's set this to linear. Set this to linear. Start frame. Okay. Let's clamp this into an integer. So we just say int start frame, and then we cast that as an integer, start frame. And then we just say frame. And we run this f at start frame. So that goes reverse, zoom, but we want the reverse of that. So we just adjust the ramp and we go boop, zoom, zoom. I don't want the zeros as well here, so I'm going to say, how do I remove the 0? Oh, that's fine. So all I'm gonna do is say if our mask attribute is less than 0.1 maybe, then we remove those two, so we don't get that extra bit. Cool. Now we can just change the values for these, set how fast we want to expand our ramp. But that's only for our emitter, the timing for our emitter. What we want as well is our flow map. So all we want to do is just compute the gradient of our gradient map, and that's done with a wrangle. So we will say call start frame, and then we say do start frame, and here we just calculate our gradient. So the way I calculated the gradient is by computing finding our neighbors and checking whether where they are in position relative to me, and create a vector from that, and then multiplying down that vector with the value, the difference between the current point's gradient and that neighbor's gradient. So in other words, we just say start points. First of all, we want to grab all of our neighbor points. So we need to have what current geometry we want to run through, the position of our current point, and the maximum distance and the maximum points. So we just initialize our maximum distance, so float max dist, max distance, and max points. So with the near points, we just say 0 at key, max dist, and max points. So that's that. Now we just have to iterate over all these points, array of points, because near points gives us an array of our neighboring points based on the distance threshold we set and the amount of points we've set based on those rules. So we do a for each, and a for each loop is basically it runs through an array. So we don't have to do any fancy count, maximum count, and things like that with a for loop. So we just put down for each, and we put in pt, and then the array that we want to run through, which is the pts. Put that in a curly block, and first I want to find the position of my neighboring point. So that would be point 0, position, and the point, my neighbor's point number. And the next thing I want to look for is the value of the attribute. So we know that our attribute is a float attribute, so we put float, and just put val, and we put 0 and what the attribute name is. So we give ourselves some nice little help. So we put string adder, and we're gonna say chs attribute, and this is the attribute that we wanna compute the gradient for. Okay, so with that, we just copy this string adder and we put it here, and we put points. So this will throw an error. Oh, it will not throw an error, but we'll just set some of the values. So we put mask for our attributes, and maximum dist, probably let's try 1.5 units and maybe 150 points. Cool. So this is not doing anything right now. We're not setting any values, we're just reading some values. Cool. So next thing I want to do is find create a vector that's between me and my current neighbor point inside the loop. So I'm just going to call that B, and that will be, I'm just going to normalize that because we're going to multiply that down with the difference between the value of our attribute. So that would be P minus at P. And if we just put that in our normals, this won't look correct, by the way, but let's just see. Okay, cool. So the next thing we do is I'm just gonna put the normals here, and we wanna find the difference between the current neighbor points in this for loop block with my value of the attribute. So S, and we say, so we already have the val, and S will be the difference between our current value and with our attribute. So all I'm gonna do here is do an F at, and because we've already set this string attribute, variable here, all I want to do is just copy this thing and then put it here, but this will not work, so we need to enclose that with a backtick here and a backtick there, with that. So there's that, and I want to multiply this direction with this difference in value. There we go. And we'll check our normals now. It's hard to see. Let's just multiply that a little bit more just so we can visualize it better. Maybe 5. Cool. So that looks a little bit better. If you can see, if we increase the amount of maximum points that we want to check. So this is quite rough because we're just overwriting our vector with whatever point that we're looking at. So what we want to do is accumulate this for every neighbor point that we find. So all we need to do is first we have to initialize our vector. So we just put, we're just gonna put vector grad and do 0. So we've initialized that. I'm just gonna put grad plus equals d times s. So now if you wanna look at what that will look like, we just put equals grad times 25. Oops, that's a bit too strong. This one, maybe 3, 4. Okay. So now we can see once we accumulate the number, we can see a smoother result between our flow. So now you can see it's a lot more smooth. We're not really just overriding our vector, but we're accumulating it over time. Over each of the individual neighbor points we have around us. So even this, we can see some flow. Super nice flow because of all the gradient that we've created. And with pighead as well. Pretty cool. So that's that for create gradient vector. All right. So we've got that, and we have this start frame remap and calling those start frame. So we can put this down in a popnet. And if you just have a look at our popnet, and I set this to all points, 1013. Zoom. It's set to normals, right? Yeah. So I'm just gonna do a point velocity and just convert that to from attribute to velocities. Zoom. Zoom. Boop. It's not quite right. Right, so our gradient is in the opposite direction. That's fine. So we just have to invert that. So we just say grad times equals -1, and that will just invert the direction of our vector. So play this in our popnet now. There we go. Boom. And what I did as well, I think in the popnet in the original sim, inside I did some stick surface. It's pretty simple. I'm just gonna copy the pop force I have here, and inside here, put down the pop force. Let's have a look at that again. Let's view this here. Pin this here. So all I need to do is, because it's coming off of the surface, I don't really quite like that. Oops. I just want to have a sticky angle. So if you put down the original geometries with the polygons into the second input of our DOPNet, and we say in the pop wrangle inputs, I'm going to set the input to the second geometry and just say add p equals min pos of 1, oops, and p. You have a look at that. Oops. View this guy. Now it's sticking to the surface. Zoom. Boom. If you don't really want it to stick to the surface, but still kind of stick to the surface, we just do a vector stick boss. We just do a small blend between our current position and the sticky position with 0.8 maybe, or 0.5. It should still come off. Oops. Get back there. You can see that the edge is still coming off a little bit, even on the y-axis, even on this guy. Cool. Maybe just a bit as well, 0.25. And you can see it's kind of coming off now. If you like that effect better, set a lot of velocities, and then give a pop drag. I'm just playing around right now. Wow. Cool. Maybe 1. Nice. That's what I like to do a lot. I give a lot of velocities at the start on the source, but give it a lot of drag as well. So we get that quick movement at the start, but with a quick fall off on the movement as well. And that gives some good impact to our sim. Cool. All right, so that's that. And have a look at our little sim here. Zoom. Boom. Boom. Cool. So we'll talk about how we source this into Axiom in the next video. Bye.